had trouble with this headset at one point, and then it started working fine, so I just wanted to make sure. Okay, what I'm going to do today, since we've had a week off at there, we've only had a week, is I'm going to kind of look at this is the 8051F020. We're using the F850, which is a scaled back version of this processor. So everything in today's lecture is not in the processor we're using right there. So now, we already did a lab in this class, didn't we, where we connected to the board? Yes, I remember doing that. So okay, that's it. Come on in. I'm not locking the door today. It's only during lab sessions I'll lock the door when I get that there. So that's it. I probably won't have a lab scheduled for Wednesday. The reason I was asking about Wednesday was simply because if I come in here and this room is empty, I'm going to be frustrated, because otherwise, if people were going to be going home early, I was just going to record the lecture ahead of time. That's there. So let me know if people are going to be leaving before class on Wednesday. If that's going to be the case, I will make arrangements to post the lecture online. That's there. Oh, somebody already locked the door for us. I didn't mean to lock the door. Yeah, that's there. No. Today I didn't lock the door on you. That's there. You were looking at the clock and going, I'm not that late. That's there. It's only on days that I schedule labs that I lock the door. And the reason I do that is so that I don't have to repeat the briefing for the lab. Lectures, to be honest, I don't really care whether you're on time or not, because if you miss part of the lecture, I record it and you go back and pick it up, or you just miss the material. So and you'll miss that question on the final exam if I cover that something that's going to be on the final exam. So all right, let me kind of go through here and try to get back to where we're at there. So basically, this says it's the second lecture on the. I guess before this thing works, I need to plug in the little Bluetooth, or the little. Let's see. That there. Okay. All right. We're going to kind of go through here on the. Again, as I said a minute ago, the C8051 F850 is the processor on the board we're using. This particular processor is the one that's set up on is the one that the university board that Silicon Labs makes, that they give away to U.S. universities, but I can't seem to manage to buy them for here. So as a result, I'm using the slides from that there, but we'll be using a different board. So when we do the labs, we have to change things around on the labs for the boards we've got. Pretty much everything else is the same. The big difference is the number of pins we have available, in that when we actually do the labs, this particular board has 8 8-bit ports to it. We have only got about 2.5 8-bit ports available to us. That's there. And as a result, our analog digital converters or digital analog converters, comparators, are all there, but we have to, this room completely over full. I wondered if that was going to happen. That's there. Go steal a chair. Next door, that there. This could be an issue on labs. Can we get into any of these rooms next door? Yeah, actually, just steal 2 of these chairs right here. Just put them back in the hallway when we're done. That's there. So, standing room only. That's there. Okay. I had a lot of people want to add this class after it was full, and I was afraid that we may overfill the room, and we did. But we can still make it work. That there. That there. If we're twice as large, the labs will be. We may have to double up on the labs. That there. So okay. And we got one row's got 5 people, and every other row's got 3. Okay. No. Okay. We've got 2 rows with 5. So we're definitely full. That there. Okay. Well, again, if we double up on the labs, and I found that students prefer to double up on the labs, because if you submit one lab report for a pair of 2 or 3, then that's okay. All right. We're going to kind of go through the memory organization. Some of this, if you took the microprocessor class with me is review. And the reason I'm going through this again is some of you took the microprocessor class with the 8086, as I understood. That there. So this is very different than the 8086. That there. So, and we didn't get in the microprocessor. We didn't get that deep into the special function registers, the I/O ports, and the crossbar. So we're going to go a lot deeper. That there. So, okay. As we look at this right here, this is the basic 8051 microprocessor as put out by Intel. The CPU is the CPU that there implements the standard 8051. So Intel put out the 8051 back, and as I said, back like 1980, 1979. I can't remember what year it was. I forgot what I had for breakfast, and that was only 2 hours ago. So actually, I do remember that there. But still, the point is it's not important what year the 8051 came around. It's an old processor. It's older than anybody in this room, except for me. That there. Yeah, obviously, I'm the old person, and I was in college when it came out. So that tells you how old it is. That there. So there. I got out of the Air Force in '78. I started college about '79, and the 8051 wasn't out yet when I started college. So it was a brand new processor. When I first started taking my first microprocessor course was on the 8085, which was the second generation. The 8080 was the first. The first microcontroller was the 8048, which you can't find anymore. Then the 8051 came out later. I think I mentioned before the 8051 was introduced predominantly for the automobile industry. You know, Intel designed it basically with General Motors in mind. And General Motors does make cars that are sold in Malaysia. Chevrolets are sold there. Opel, I don't know, is Opel still sold in Malaysia? It used to be sold in Malaysia, because I had an Opel back in the 1990s here. That's a General Motors vehicle. But General Motors had the problem where they had to meet emission standards in the U.S. and in Europe in order to make fuel-efficient cars. The only way to do that was to have computerized control ignition systems. So the 8051 was designed with the automobile industry in mind. The since then has been used for far more. But that was the initial. So as we look at this right here, we'll kind of look at the basic architecture. We'll get into more detail. We've got a couple from the processor or from the programmer standpoint. If you're programming an assembler, the two registers that you see most often are the accumulator, which is the A register, right there, and the B register. There's only two registers in the processor that are addressed as that there. Now, we also have a bunch of other registers in the processor, but they're stored in the static RAM inside the processor. So they're not actually separate registers, they're actually memory locations in static RAM. And static RAM in this particular case is RAM that's the power is lost whenever you shut it off. So then we've got going down here, we've got this data bus here, which the data bus, as we talked about buses before, connects to everything on the processor. Memory, I/O, that's how data moves in and out of the processor. The ALU is what does the adding, the multiplying, the dividing right there. An output of the ALU is something called the program status word. And we'll see this program status word quite a bit because that's used to test whether or not you have a zero output. If you do any kind of looping, you'll use that there. If you have an overflow, that's there. So the ALU tells it that there. And what's inside the program status word is a series of flags, and we'll talk about the flags in a little bit more detail, right there. So these two temp locations, we don't address them. Those are internal. We don't address those immediately, right there. So down here we have a series of registers here internally that we don't necessarily. That's there. One is just a buffer that just simply is a place where data is stored as it's going in and out of memory, right there, temporarily. We have the data pointer. which points to data. It's actually what it is. It's a register that we will use for indirect addressing. We have the program counter incrementer. Every time we come across a instruction, we have to increment the program counter by either 1 byte, 2 bytes, or 3 bytes, depending on what the instruction is. Right there. So we have that there, and that looks at the current instruction and determines where the next instruction is going to be. Right there. So we have the program counter, which then, of course, is incremented by the program counter incrementer. Right there. And the program counter is the next address in memory, program memory, that's going to be accessed by the microprocessor. So this points to our next location in memory that the microprocessor is going to get its instructions. And then we've got the program address register, which is just basically a register to keep track of there. So these are basically a bunch of registers that are used for various types of activities in keeping track of where to point to data, where our current program is, those types of things. Now, as we come over to this side over here, we've got something called the special function bus interface. These special function registers are locations that are actually stored in the static RAM, internal RAM memory, and these are, when they say special function, means that they have a special function. A special function might be something such as port 1 is a special function register. That's there. So port 1 has an address. It's actually 8 pins on the output or input of the processor, depending whether you're using port 1 as input or output. Right there. We may have another port that sets up whether port 1 is going to be an input or output. Now, port 1 happens to be bit addressable, so we can also address each bit in port 1 at a time. Some ports are bit addressable, some are nibble addressable, some are word addressable. Now, as it turns out, the ports we're going to be using, because of the small chip, they're almost all bit addressable, because we've only got the 3 ports that we can address. Actually, our pin's got 22 pins, so if we talk 8-bit ports, that 3 times 8 is 24. We can't address full 3 ports. We can address up 2.5. And remember, we also lose 2 pins for VCC and ground. Right there. And if we want to use other devices, we'll look at those. So these are our special function registers, and there's about 128 of those. And those are how we configure this processor, how we interface to it. Then we've got something called the memory interface. Now, the memory interface is really designed more to access external memory. Now, we're not going to be accessing external memory with our particular processor, but the 8051 can interface up to 64K of external memory. And the external memory is typically going to be used as program memory. We'll talk a little bit more in detail there. So, yep, come on in. You're going to have to get a chair. We're out of chairs. I think there's a couple more chairs to the left there. That's there. So, that's there. So as we look at our memory interface, we'll talk a little bit about that there. Yep. Oh, this room is going to be over full. That there. I may have to look for a bigger room for the lecture here. That there. Our lab is going to have to be in here, but okay, that's there. Okay. So our memory interface, that's there, and we'll look a little bit more at the memory of this particular device, because it is different than the 8086. That's there. And then we've got some control logic there, and basically that's the reset in the clock right there. And then we have a stop and an idle control in order to save power. This is the basic 8051 that is designed by Intel. Now, when we look at the F020, which is similar to ours, what you'll see on that there is that we have in here, let me find my pen here to circle, right here. right here. Right here. This little box is what was on the previous slide. So as we look at this previous slide right here, this slide here, that's the internal CIP51. That's the basic core for the 8051. When we look at the F020 or the F850, you'll see that we have, that is right here. One little tiny block in our overall processor. So our total overall processor has considerably more added to it right there. So when we look at this right here, we have a series here for digital I/O. Our digital I/O, of course, uses the crossbar, and we'll talk a lot more detail about the crossbar right there. And as you can see, they show 4 I/O ports. These are 8-bit pins. And down here we have 4 more. Now the F020 is a 64 or 100 pin device. Our device is 22 pins, so we don't have as much. So what they're showing here in this diagram is that if you have the 100 pin device, you have 64 pins of digital I/O. You have 100 pins to work with, so you have plenty of pins. If you have only the 64 pin device, you only have 32 bits of I/O right there, which is quite a bit of I/O for a control application right there. You know, our particular processor, we have about 16 bits of I/O, which again is quite a bit. That's a lot for the type of processor here. So something the original 8051 did not have is a series of analog devices right there. And we'll talk, last semester, those who did take the microprocessor course, we did not get into the analog at all. We will this semester right there. As we look at this particular one there, we've got what they call a analog mux. This analog mux allows us to have up to 8 analog inputs, and we select which one we want to go through there. Now again, our processor has 22 pins. If we have 8 analog inputs, that's 8 less digital inputs we can use. That there. The job of the crossbar, and I think it was one of the final exam questions last semester, was what was the purpose of the crossbar? And it was to decide, to program which peripherals we're going to use to what pins on the device, right there. So when we look at this crossbar, that is used to determine right there. So we got the analog muxes. We got a couple of these right here. We got a couple of analog or digital to analog control converters, so we can get analog outputs right there. We have a couple of voltage comparators that will look at 2 pins, and if one is higher than the other, it will give us an output. You know, at there. We have a programmable gain control, which we'll talk about much later. We'll get into that there. Of course, we have to have a reference voltage. Built into the chip is a temperature sensor. That's actually built into the chip, so we don't use any pins for that. That there. And we have 2 analog to digital converters in this particular case. One is a either 10 or 12-bit 100 this is 100 kilo samples per second is what that symbol means. In other words, it will take 100,000 samples per second right there. This one here is an 8-bit ADC that there, and it will do 500 kilo samples per second, roughly 500,000 or half a gigahertz sampling rate. So it's a very high-speed analog digital converter right there. So, and that's the reason why we've got multiple muxes, is that we got 2 different ones. I can't remember. I think ours may only have this one here. Ours may not have the 500 kilo samples per second. We wouldn't use it if we do. We'll use this one here. There, we won't use the high-speed one right there. So, right there. Now, when we get into the core down here, we've got some other things. Now, ours does not have 64K of in-circuit programmable flash memory. That there, it's got about 4K of programmable memory. That's where our program stands. We don't have quite 4K of RAM, I don't think. I can't remember how much RAM we've got. We'll look at that later. But this is built onto the chip right there. So when we look at the 8051, we'll see ours up there. We have a bunch of interrupt possibilities up there. I don't think we have 22 because we only have 22 pins, but these are all interrupts that we could set up for this microcontroller. The key thing we've got here is this is unique to the Silicon Labs, is we've got our in-circuit debug circuitry that allows us to single step through our code. We saw a little bit of that in the lab where we could go through and set breakpoints, stop our code, look at registers. We also have our JTAG debugging capability out there for programming. And JTAG does more than just do debugging. It does power on checking. It goes through and checks every circuit on the IC, makes sure it's working right, generates errors if there's problems out there. We also have something called the clock circuit right there. We'll talk a little bit more detail about that. Those who were in the 8051 class or the microprocessor class, we talked quite a bit about the clock last semester, but for those who are new to the 8051, we'll go through that again. So those who had the 8051 with me last time, you'll see a little bit of repeat. And you'll probably see some of the same questions on the final exam, which is probably good for you, right? Right there. So, and then we have this one here, and this is called sanity control. We won't get into much sanity control. Sanity control is that there. So, that there. But this is a mixed signal system on a chip is the way that this is named. Mixed signal means that it's got both analog and digital inputs and outputs right there. The 8086 or a general purpose microprocessor will not have any analog inputs right there. That's unique to certain microcontrollers right there. So that there. And a system on a chip is a terminology that has come up more recently, the term that there. It means that this is a complete system on one chip. It has everything you need for a full controller on the single chip. It's got the CPU, it's got all the peripherals, it's got the clock generator, it's got everything you need is on that single chip. If you look at the board that we did the lab with, the only thing on that board essentially was the microcontroller. There was a couple other things, the two push buttons and the two LEDs, and that was basically it. There wasn't a whole lot. If we were to pull that up, that's there. And if I can find it, you know what? It's easier to find here on desktop. Right here. And as you can see, this is our lab development board. And as you can see, there's only what? Here's the microprocessor right there. There's our 22-pin device. This is a potentiometer for testing the analog port so that we could do an analog lab without connecting anything else to it. We have two push buttons for doing tests right there. And they're tied to port 2.1 and 1.7. And we have two LEDs. That's the only thing we have on here. We have a jumper here for telling it where we want our power, because we have the option of doing our power, wiring our power here, or bringing our power in from here, right there. When we're doing it with a programmer, we would use our power. If we were to develop a board for this and want to use this for a system, which you probably wouldn't, you would only use this for testing and debugging in the lab, you could actually cut these off and just program the chip and cut that off and put that in your system right there. So, and there are people that do that right there. They would just cut this off and they would just bring the power in here. And that's what this jumper right there is for right there. So, going back to my slides, slideshow, from current slide. All right. So this is basically the processor we're going to be working with, microcontroller. Right there. So these are the kind of the features. Again, this is for the F020, not the one we're using, but it's the one I'm going to use for our lectures right there. And as we can see, it's got built onto it right there that it does 25 million instructions per second. That there's its peak throughput. It's got 64K of flash program memory. The original 8051 had 4K right there. It's got 4K of RAM. Actually, it's 4K plus 256 bytes right there. That there. The original 8051 only had 256 bytes. That causes some headaches. It's got 2 UARTs right there. When we say UARTs, those are serial ports. We're talking to other microprocessors, talking to terminals, talking to modems, things like that. It's got 5 16-bit timers. Ours actually only has 3, I believe, right there. I already talked about the 64 pins of digital I/O, which again we mentioned we don't have that many. We've got 8 channels of 100 samples per second, 12-bit, and 8 channels of 8-bit at 500 out there. Now these go through analog muxes. There's not 8 analog converters there. You can only do 1 conversion at a time out there. You could have 8 inputs and you select between that there. We have 12 bits of digital analog conversion output, 2 of those, 2 converters. We have 2 different levels of interrupts. We have our programmable counter arrays, which we won't get into, and we also have the internal oscillator and debug. So this is everything that's in this particular processor. That's there. So now if you look at this processor and you compare this, say, for example, a ARM A7 processor or A9 processor that's used in, say, the Apple phone, it's not very powerful. But if you compare this to, say, for example, a low-end PIC, it's very powerful. When we look at PIC processors, they tend to be about the least powerful but the cheapest ones. The 8051 is somewhere in between. The ARMs tend to be more powerful, more complex right there. Which one do we teach here at this university? Well, we're teaching one that's somewhere in I'm teaching one that's somewhere in the middle up there. And really, the reason I teach this one is because the software tools are the best. They're the easiest to use right there. The PICs aren't bad, but they're not right there. The ARM tools are quite a bit messier to use right there. So, okay. Now we're getting into an ugly diagram. This is an ugly diagram right there. However, this is the one that kind of shows how everything works internally. And I don't know if I can do this here, but as we go through this, and I'm not going to expect you to memorize this diagram, but I want to go through all the steps here at there. And I know that I went through some of this before, but with those that there, I don't think I did this semester. I haven't gone through this diagram yet with you guys. If I did, I apologize, but it's been over a week and you probably forgot it anyway. Right there. So here's our digital power right there. That's our digital power in there, and these are our grounds. Now, this shows 3 inputs. That's because the 100-pin device has 3 different ground pins on it. That there. Ours will only have 1 ground pin right there. So we got an analog power right there, and the reason we have our analog power is because we have A to D's and D to A's, so we have to have an analog power. Typically, they're hooked up to the same power source right there. Right there. We get into our JTAG interface right there. These 4 lines right here are the ones that plug into the little programmer module. We go back to right here. Those are the 4 lines. Those 4 lines get plugged in right here, right there, right there. So we've got a reset line here. That's there. There's multiple reset sources right there. The most common one we will use is the reset NOT. That comes from the outside world right there. And we have another reset here, which we'll talk about. We talked about it. I talked about it in the 8051 version of the microprocessor class. We didn't use it. This semester we'll use it. And that's the watchdog timer. Right there. All we did in the initial 8051 course, because the purpose of that course was to introduce microprocessors, and we didn't get into great detail on interfacing into the outside world, so we did not talk about the watchdog timer. We talked a bit about its purpose, and as I recall, there was a final exam question that said, what is the purpose of the watchdog timer? And give an example where you would have to use it. That's there. But we didn't actually write any code for it. Right there. That's there. So this semester we'll get to write some code for it. Right there. Those who took the 8086 version of this class, you probably never heard of a watchdog timer, right? Anybody here who took the 8086 version of this class, or the microprocessor class? And last time several of you, did they ever mention the watchdog timer in that class when you took it? Do you ever hear the term watchdog timer? No, I didn't think so. That there, because watchdog timers you normally don't see in general purpose microprocessors. That there, you see it much more often in embedded systems. That there, and I'm gearing this course again toward embedded systems because as electrical engineers, you're 99% more likely to see an embedded system in your line of work when you graduate than you are a microprocessor-based desktop computing system from a design and troubleshooting level. Right there. If you go out into a factory floor and you look at the PLCs, the assembly line controls, you look in a power plant, you look at all the monitoring systems, they're going to be embedded systems for the most part. So that's why I'm concentrating that there. And that's true even in the U.S. That there, 95% of all processors in existence are embedded systems. That there. So that there. And I know I talked a little bit about the difference between embedded systems and desktop computers in the first week, but that's there. But just a quick review again. A general purpose microprocessor is a desktop computer. This is a general purpose microprocessor base. That's there. When we look at the engine controller of your car, the dash of your car, DVD players, those are all embedded systems right there. So you're going to have something called the watchdog timer. And the purpose of the watchdog timer is to reset the processor if it gets locked up right there. So it feeds directly into the reset pin right there. And I should note that this is an active low input, and the output of this is an active low. So if either of these goes low, the output of this AND gate is going to go low. So, and that's going to reset the 8051. Now, in the 8086, in other processors, you had an external clock that you had to bring into the processor. With the 8051 family, that it has an internal oscillator here. And we'll talk a little bit more about this. My hand doesn't show up here. Right. Let me use my mouse here. The little oscillator, the internal oscillator means that we don't have to have an external oscillator circuit. We could, if we want to, have an external oscillator. Right there. And there are times when we want an external oscillator. And we'll talk a little bit more about that. Again, I know with the one class I did, when I talked the microprocessor version that I taught last year, I talked about the internal oscillator versus the external oscillator. All right, we have our V reference. We talked about that. We have a V reference to our digital D to A's right there. And these are our 8 analog inputs going into our 100 megabit or 100 kilo samples per second, A to D, 12-bit right there. And notice that one of our inputs to our analog mux is the internal temperature sensor on the chip right there. We have our 2 comparators right there. Again, these pins are not necessarily available unless we run through the crossbar right here. Then as we go on the other side, here's our 8051 core at the center of this. We've got our memory right here. Now, as we look at the memory, it's kind of interesting. We've got 64K flash memory. That's our program memory. We've got 256 bytes of RAM. That's internal memory. And then we've got 4K bytes of RAM that is actually connected to the external data bus. The RAM in the memory is a little confusing on this processor right there. And I'll make these slides available, by the way, on Facebook right there. So those who are trying to write these down, I'll I'll make them available. Actually, the book in which they came out of should have already been put on Facebook. Has got that there. So, okay. So then we get into the special function registers right here. And our special function registers are all going, everything here, right here, we have coming down through here. And I'm only going to worry about the top part because the bottom part we don't have on our processor right here. So I'm going to skip that bottom part here. The top part here, we have this crossbar. This crossbar switches between here, we've got 4 analog ports right there. Now notice something right here. And it's a little hard for you to see. Let me blow this up. Yeah, I can't blow it up any more than that. Port 1 is, if you look at port 1, you'll see AN1.0 to AN1.7 right there. That goes back to our, this shows our AN0 as separate pins. This one here shows going to our analog ports right there, to our 5 kilosamples per second. They share, those 8 pins are shared with port 1. So if you want to use those analog pins, you have to give up port 1 right there. And that's part of the programming of the crossbar. Now, our particular processor does not have these separate pins down here. So what we have to do, if we want to use the analog, we have to give up one of our ports. Now, as it turns out, we can give up 1 pin of a port, 2 pins of a port, 3 pins of a port. We can do it pin by pin, but we share the analog as shared with the inputs and outputs. Same thing with the UARTs. The UARTs are also shared with these pin ports right there. The SM bus, the SPI bus, PCA, all these are shared with the ports there. So the purpose of the crossbar is we've got a series of pins out here in the real world, and it decides what gets connected to those pins. We've got 22 pins, well actually 20 pins that we can use because we lose VCC and ground. And if we use an external clock, we're going to lose 1 or 2 more pins. So we have to decide what we're going to use. Now we're going to probably use the ports most often, right there. We'll probably do one lab where we're going to use the analog, right there. So the goal here is we're going to be connecting keypads, LCD displays, temperature sensors, things like that to this device right there. So, and again, as I said, I'm going to skip this down here, right there, because we don't have that on our chip. So as you can see, this is a fairly complex piece of equipment that there for something this big. We have a lot inside there. There's a lot of stuff inside that chip right there. And the goal of this semester is to figure out how to use most of it right there. So, all right. Okay, now, getting into a little bit, and I know this is review for those who had the microprocessor course, but I'm going to go through it again, because as I recall, some of the results weren't that great on the final exam at there, and it's also been, if you took it last in the January semester, it's been a while since you took the course, so you probably forgot some of this stuff. Those who took it in the short semester, it's probably still pretty fresh in your mind. There are 3 different address spaces in the 8051 family. There's 3 different address spaces right there. Right there. Okay. One is the program memory. This is where we write our code. Right there. When we write programs and we download it to the board, it's going to go into this flash memory area. Right there. And I can't remember exactly how much memory we have. I think it's 4K of flash memory we have for that there. Now, embedded systems typically has far more flash memory. The F020, the one that this book is geared around, has 64K. We have considerably less, that there. And I could probably we'll pull that up later on, probably not today, but we'll see exactly how much memory we have to work with on our chip right there. But it's somewhere right around 4K, 8K, something like that. It's not a full 64K right there. So as we look at this particular one here, we got program memory, then we've got data memory. Data memory is the internal address space right there. And then we've got external data that's there. So our internal memory is only 256 bytes, of which a lot of it is not usable. Right there. And the reason it's not usable is because this right here is our R0 through R7 times 4 right there. The 8051 allows us, as I said, it only has two registers, A and B, right? That's not enough. So we have to use R0 through R7 as registers in order to do adding, multiplying, dividing. And those are actually stored in the static RAM area, internal address space. And they take up the first 32 bits or bytes of that memory. That's it. So if we use R0 through R7, which we will, that's there. Now a lot of our programming is going to be done in C, and we won't see how they're used. That's there. But we're going to start off by writing a couple of assembly language programs, and then we'll move into C right there. That's there. Then we've got another 16 bytes there that are bit addressable. Now they're either byte addressable or bit addressable. So those are general purpose RAM that we can use for whatever. And then we've got the rest of these up to 128 that is just general purpose scratch pad RAM that we can use for whatever we want to need RAM for. So that's our bottom 128 bytes of RAM. The upper 128 bytes are where our special function registers exist. We can't use those. You can't use those for anything other than what they are. That's where port 1, 2, 3, 4, 5, 6, 7 reside. That's where your analog digital converters, where you read the output of the A to D. It's where you're going to put the output for the D to A. It's going to be where your timers are. All that stuff those are special function registers. We use those, but they talk to the peripherals. This is really not RAM in the sense of RAM right there. It's the peripherals on the device. All these peripherals that we're looking at here, all these peripherals right here go through the special function registers along with all these right there. So all those go through the special function registers right there. So if we want to program our watchdog timer, it's got a location in the special function registers. If we want to set up our clock, whether we're going to use an internal or external clock, we're going to write to a special function register. This is where we program. This is where we set up everything. Anybody that's ever fooled around with a desktop computer and gone into the BIOS and you go through all the settings to set up a motherboard the correct way, that's really the type of thing we're doing here. This is how we set up our chip out there. And that's normally done in the initialization routine, which we're going to set up our chip the way we want it to be set up. Because, again, this chip has a lot of stuff on there. Not every application is going to use everything on this chip. Matter of fact, you can't, because the number of pins you have limits you on what you can use. We've got 20 pins essentially to work with, and we've got enough peripherals to drive probably 64 pins. So we've got to decide what we're going to use and not use right there. The timers don't necessarily use pins right there. The watchdog timer doesn't use pins, but the A to Ds, the D to As all use pins right there. The ports all use pins. The serial ports use pins. The ESM bus uses pins. Some of the timers will use pins right there. So all that configuration is done in these special function registers. And incidentally, there's a book out right there. I'm going to kind of pull it up here. right here. See if we can pull up here. If I can find it here. Right here. This is the data sheet for our microprocessor right here. Right there. And our particular microprocessor here is part of the family right here. And you can see it's got a little bit different setup there. It goes between 2 and 8K of flash. The one we just had up showed 64K. It's got between 256 and 512 bytes of RAM internal right there. It's got our serial debugging. It's got our clock selections. It's got, here's our 12-bit 200 kilosamples per second or 800 kilosamples per second. Actually, it's a little faster A to D on this one right there. Voltage referencer, 2 comparators. It's got 4 timers. It's got 1 UART right there. So you can see it's a little bit different right there. Right there. But as you go through and look at this, this particular data sheet is 294 pages long. This is a very boring document to read. Right there. As you go through here, this is the document that tells everything there is to know about this processor. You know, right there. This goes through here. I need to unplug this a second here. What I want to do here, okay. Right there. Okay, what I want to show here is that right here, when I mentioned the special function registers, right here is the start of the special functions. This lists all of our special function registers and where they are in memory right there. And for example, P2 is at memory location A0 right there. P1 is at location 90. P0 is at memory location 80. So, right there. So this shows where they're all at right there. So this is a 294 page document. And this kind of goes through and it gives special function registers that there. It goes through and explains each and every one of these and what they mean. Port 0 mask, port 1 match, input mode, right there. So this goes through all our special function registers right there. And trust me when I say that I have read this document many times, because whenever you get a new processor and things don't work right, you go back to the data sheet and you read it for the little gotchas right there. What's that? The list there? Right here. Yeah. This is used for programming. In other words, if I want to look at timer T1, it's an 8-bit timer, I would look at these particular locations right there. If I want to set up the mode for the timers, I would look at these locations. If I want to output something to P1, for example, right there, I would do a move P1 comma whatever number I want to send out to that port right there. See, and this is the port P1 location 90 is port 1 pin latch. In other words, that's what's going to write to the port right there. So, and we did some of that. Now you can also address these by bit, P1.1, P1.0 right there. But what that's saying is it's writing to that location right there. You don't have to use the addresses as long as you include that there. In other words, if I go back here and let's pull up open up Blinky, for example, here. And Blinky's the one that right there. And hopefully I took. Oh, I'm sorry, wrong one. Open with. It's when you open up with Code Warrior. Oh, it's still broke. All right, doesn't matter. This is the wrong compiler. This is for a Freescale product. But if you were to open this file right here, and let me find that file, and let me open that and show you that file actually equates to that there. Because this shows the green is port 1.0 right there. So let's go back here and here it is. Okay. I'm just going to open up with Notepad right there. Right there. And what you'll see here is that port 1 right here. See, this is what tells the compiler that port 1 is address 90 right there. So that's why you include that include file, is so that you can use P1 and not 90 right there. So that tells the compiler that port 1 is location 90, which goes back to this document right here. Now, what happens once in a while in life, that there, and I know I'm talking to a full room, some of you are coming, and actually I think some of you weren't here for the first week that there, so that there either, is that if you get a new processor, you may not have this include file with it. And then you have to generate the include file from the data sheet. That there. Hopefully, usually they give it to you that there. But that include file actually is what maps ADC0 THL, which is the analog digital converter 0, the high byte, less than high byte, the memory location C6. That there. That's done in the include file. Because the Kyle compiler that we're using, and Kyle is a company that writes compilers. They're like the Microsoft Visual Studios compiler. But the Kyle compiler writes code for every 8051 family out there. And there's many, many 8051 families out there. Silicon Labs is just one of them, if we went through that there. You know, Atmel makes an 8051, Resonix makes an 8051, Philips makes an 8051, and they all have different peripherals. Thus, they have different special function registers. That's there. So Kyle is a generic compiler that will talk to all these different devices. In order to tell the Kyle compiler where memory location P1 is, we have to have it listed in that include file I had up a few minutes ago. So going back to your question, when you program, you can use P1 because the include file points to it right there. If you didn't have the include file, then you would have to put the memory location for P1, and it would make our code so much less readable. You don't want to do it that way, right there. You don't want to do it. You want to use the include file and use the names. That's there. That's there. Yeah. As a result, I don't require that you know the memory locations of P1, P2, P3, or that there, because it's easier to just remember P1. It's easier to remember TL0, TH0, which TH0 is the timer 0, the high byte. TL0 is timer 0, the low byte, right there. It's a 16-bit timer. It's easier to remember those names than it is right there. And as you can see, the special function registers, and if you look at this table, by the way, this tells you that if I want to look at this special function register and how it works, I go to page 160, and that tells me in great detail how to program that special function register right there. We didn't get into any of that last semester, there. We didn't get into, because that was an introduction that there. This semester we'll get into some of this right there. So this document is a very boring and tedious document. And he's fallen asleep already, and we haven't got into the meat of it. That's there. So we're picking on you, that there. But that's it. But regardless, I understand that nobody likes to read these documents. Now, I don't like to read these documents. But I can guarantee you, when I've sat with this processor in a system and something's not working, I go back to this document and I read carefully those special function registers, because each special function register has to be written to a certain way with certain bits in certain locations in order to do it. And this is the document that tells how that's done. This is the PCA mode. And this tells me that bit 7 specifies behavior when the processor is idle mode. So PCA continues to function normally when it's in idle mode, or the PCA functions suspended when it's in idle mode. So again, you have no idea what that means, but if I'm trying to use that PCA that's there and I'm trying to program it, I need to know how I program it, and I have to look back at this document. And it's a 300-page document, as you can see, and it's not very user-friendly. And I think I've probably given this class a little discussion, or that the reason why English is so important for electrical engineers is all these documents are only available in English. That's there. And they're also not only just only available in English, they're written in English that only engineering types can understand and read. So it's not an easy document to read. That's there. I've had more than one student whose native language was English look at these documents and go, oh, that's there. I am not going to expect you to be able to read and fully understand everything in this document, but I will refer back to it from time to time when we start talking about setting up the ports, for example, as inputs and outputs, and setting up the controllers. You see, we get into, for example, our PWM timing right there, how that works right there. And this goes into center aligned PWM, how we set up our duty cycles. You know, we got edge aligned PWM right there. So, you know, and PWM is pulse switch modulator right there. So we've got all kinds of things. If we want to control a stepper motor, we use pulse width modulator. So if we want to run a stepper motor, we're going to have to read this section right here. How do we program the frequency of our pulse width modulator? How do we set up our duty cycle right there? How do we set up to be either edge or center trig right there? So duty cycle is equal to right there. You know, again, we're going to set this up, and as a PW resolution right there. So again, we get into how do we make those calculations in order to, you know, I've done labs where I've made, you know, I had students design little robots, for example, you know, little cars that would go around a track, and we would use two pulse width motors, and we'd have to adjust the speed. They would both go the same speed to go straight. The one that to turn left, the left motor would shut off, and the right motor would continue to go, or the other way to turn right, or we could go reverse. So we could program motors using this pulse width modulator right there. So in order to do that, we have to read this nasty little document to figure out what to write and what modules in order to get this motor to turn left, to turn right, to go straight right there. So we'll get back to this document from time to time, unfortunately. Right there. How am I doing on my time? Oh, we got plenty of time. At least 20 more minutes, right? And for those of you who are this is your first class with me, I do not talk for 2 hours. I'm looking around this room and people are having, after 1 hour I see people starting to want to doze off. After about an hour and 15 minutes, I start to want to doze off. So, so I'm about 75 minutes up there. Okay, getting back to this particular set of slides here, and I will put these slides online at there. But again, the key takeaway here is that when we talk about memory organization with microprocessors, there's two types of processors they talk about. One uses what they call Harvard architecture, the other is called von Neumann architecture. I didn't talk about that in the microprocessor class and I don't know if the 8086 person talked about von Neumann versus Harvard, but let me just kind of make a quick, I'll probably misspell them there. But when we look at the Harvard has separate data and code memory. This is supposed to be separate. Data and code memory. So when we address memory, we have to know whether we're addressing code or whether we're addressing memory. The von Neumann, and that may not be spelled right, von Neumann. Of course, with my handwriting, you can't tell whether it's spelled right or not. Only has one address space. So part of this could be ROM and code, and part of this could be RAM and data. There's only one addressing space there in the von Neumann. A Harvard has two separate code and memory. So, and they can overlap, or code and data, and they can overlap right there. And the 8051 uses the Harvard type memory addressing. It has separate code and separate data, but the further complicated is that it's got two separate memory addresses for external, right there, and that's going to be data. And you can have external code too, but we won't look at that right there. But when we look at there, if we're going to use external, it's called external RAM, and when we're going to address it in assembly language, we use the MOVX command right there, which tells it that it's external memory. Here, certain functions operate there, and certain commands there. So we have to specify when we write assembly language whether or not it's going to be in code, internal RAM, or external space. Now, what makes this somewhat unique is that this external bit address space is actually still on the chip. That's what makes it kind of unique. It makes it very confusing. We go back to our chip here, and we've got this memory right here, right there. You see this on-chip RAM, 4,352 bytes. What that is that it's 4,096 bytes, or 4K, external on chip, right there. And then 256 standard 8051 memory. So it's confusing. There's nothing I can say about it. It's somewhat confusing. And then the onboard flash memory, program memory, is 64K. So we've got three different addressing, three different places of memory here. We've got our program memory. This is our program memory. And this is divided into two types of memory. This is our static RAM. It's got external, where we have to use the MOVX to get to it. Or if we're going to put data in there, we have to tell it it's going to be in the external memory as we set up our variables in C, and we'll get into that in more detail. And remember, our processor right here, go back to 1, right there. Our processor, and actually, if we go all the way to the end of this document, is where I want to see. Somewhere in this document, it tells which chips have what, and I don't see it. Maybe it's here at the beginning. Let me give me a second here to find it here. As you can see, this document right here. Power consumption. Here's all of our clock data, all of our frequency information. What I'm looking for is a table that lists the various chips in the family and what peripherals they have, and I'm not seeing it yet. I'm hoping it's in this document. It should be. See, it gets into the power consumption versus frequency. I talked about that in the microprocessor class. As you can see, as we increase our frequency, our current is going up. And remember, our power consumption is the current squared. So, as we can see that there. And what I'm looking for, system overview, that gets into that same table right there, power. You can see this table gets quite detailed, but somewhere in here there should be, okay, right here, this is the 24-pin device right there. It goes through all the pins right there. This is for the 20-pin and what we've got available for it. This is the 16-pin. Maybe ours is, see, and this gets to the exact part number and explains what's in each part number right there. So, and this gets into the details of what's in each chip. Now, if we go through here, hopefully this and I'm getting sidetracked, and I'm getting to a very place where people are going to be dozing off quickly, so I'm going to stop after I get there. If we look at this particular one right here, I can't read it from that there, but it should tell me what chip is on here. Got there, continue to I don't use Simplicity Studio. And this is not telling me what chip is on there. Oh, here we go. We're using the 24-pin chip is what we're using. I said 22-pin. This is the chip we're using right here. Right there. And maybe this semester I might sit down and learn this Simplicity Studio. That looks like it might be a little easier to use than the one I used last semester. That's it. It's their new user interface. It's supposed to be easier. I'll be honest. I just use what I've been using for the last 5-10 years. That there. But as we look at this particular part right here, we're using the 24-pin part. So if we go back to our tool stick. Right there. We're using the 24-pin right there. So if we look at our 24-pin device, that's this device that we've got right here. So this is the device we're using right there. So this tells us what we've got available to us. as I said, I keep saying I said 22 pins, and it says it's a 24 pin package, but you'll notice that there's some no connects on there. So we're not using all 24 pins there. But as you can see right here, this is shared. This is shared. A lot of these are shared right here. If we look at these right here, standard I/O right there. But as we go through and see here, additional functions right here. Port 1.0 right here, port 0.1 can be used, it's on pin 3, it can be used for interrupt 0.1, interrupt 1.1, P0.mat, whatever that is. It can also be used for these analog ports. So one pin can have one of 8 different functions depending on how we program this chip right there. So, but this is the chip, this is the exact chip we're using right there. So, with that said, before everybody gets completely sidetracked and lost right there, because I see when I went off on that tangent, I started losing everybody. It's a good place to stop. Any questions where we're at? You're completely confused at this point, right? Yes. You're completely confused at this point. That's fine. Because I don't expect you to see this the first time and understand. You saw it before, so now it's starting to make more sense than the first time, right? That's there. So you're going to have to see this again, and we're going to have to start using these things before they actually sink in. If I was to give you a quiz on these pins and what they did, I would expect to get about a 20-25% passing rate right there. So I don't expect you to understand everything at this point. Right there. We're going to see this again and again. Right there, because the goal is we're going to have to use this chip. Right there. And right now we're talking about so many things, new terminology, flash program memory. What's flash memory? Hopefully you remember that from your digital class, right? Well, a thumb drive uses flash memory. Yeah, so there you know what flash memory is. Static RAM you don't necessarily use because you probably have nothing that uses static RAM, because desktop computers use dynamic RAM. SRAM, yeah. So you probably remember seeing that somewhere at your microprocessor. So with that said, I will see everyone Wednesday at there. We've got a fairly full group.